Hi, class. Okay, so today we're going to continue on with strong induction and the well ordering property. And we will finish up chapter 5 of Rosen on Monday. And then for the ensuing 3 classes, we'll cover chapter 6. And then that'll be it. As far as material that'll appear on the final exam, there'll still be a few more lectures. If I see that there's any subject that's worth reinforcing, then we'll go over that. But there's only a few more lectures that you have to worry about for the exams. And so for those of you that are eager to skip out on class and skip the material, your time to shine is coming up, right? But for everyone else, and for you as well, really, we do have a little bit more to cover. So let's dive into it. It should be another fairly quick lecture. So we begin with the well ordering property, which simply says that any finite set of or every non-empty finite set of integers has a least element or some smallest element. And this is something that is pretty intuitive. So if you have 1,000 elements or a million elements and they're all integers, then one of them will be the smallest, and there may be multiplicity or whatever. But if it's a set, then we're guaranteed distinctness of the elements of the set, right? That was one of the properties of a set versus a collection. So since they're all unique, then one of them will be the smallest. And if it doesn't make sense, try it from the other side and try to imagine a set with a fixed number of elements in it where there isn't a smallest number. Now, if all of the numbers are unique, what would such a structure look like? So it turns out that it's not possible, but it's definitely worth the mental exercise if you don't get the principle of it. That property is used in some proofs. None of the topics that we're going to cover actually goes over that. But it does kind of show up in the idea of recursion. So whenever you define something and you try to work your way backwards from it, then this principle basically says that you can reach a basis step, right? So like if you consider Fibonacci or the recursive function that we're going to look at in a little bit, then you can count backwards from whatever term you're looking for and know that eventually you'll be able to count down to 0 or whatever that fundamental value is that kicks off the sequence of terms. So the well ordering property just guarantees basically that your recursive definitions will eventually terminate. Okay, so moving on, strong induction, and I had initially intended to not cover this, but it does kind of relate to recursive functions a little bit, so I thought I would speak on it a little bit. So for induction, whenever we're proving it, we always proved it going forward. So you define the basis step, and then you assume the inductive hypothesis, and you do the inductive step, and you make the substitution, and then it shows that, well, if it was true for k elements, then it's true for k plus 1. And so strong induction is a little bit going in the reverse order, right? So again, we have some basis step, and then we have the inductive step, and it says that if we have, again, if it's true for all the way from that basis step up to some kth step, then we can generate a truth for a k plus 1 step, or a k plus 1 term, if you prefer. And so it still looks like it's going forward, right? But this is a little bit more into the idea of reducing it to something that has previously been proven to be true, right? And so the example that I want to discuss is a Rubik's Cube, right? So pull up an example. All right, so if you've never seen one, this is what I'm talking about. It has 6 faces, each with a distinct color and with 9 squares on each face. And you can rotate the edges, and you get some scrambled result that looks like this, or any of these states, right? Okay, so whenever you buy the Rubik's Cube, it comes where all of the 6 faces, each of the 6 faces, all has a single color on that face. And so if you rotate one side, then it's no longer in a solved position, but you can get back to that solved state by rotating in the opposite direction. And so back in the 80s, whenever the craze on Rubik's Cubes, kind of came out, it was irrationally frustrating, to the point where people began to ask, well, is this even solvable? Yes. We could state, using strong induction, that so long as you haven't removed the stickers and replaced them, and you've reached a state only through these rotations of the face, that it is solvable, right? And so the idea is that you start with some state, P0, which is the solved state, and then one step later, so any rotation of any face by 90 degrees, so a quarter turn of the face, achieves some new state of the cube. And you can return to a solvable state by rotating in the opposite direction. Well, by that same logic, you can jump from state P1 to state P2 by rotating any of the 6 faces, in possibly the same one that you rotated in that first step, by 90 degrees, so another quarter turn, and in order to reduce it to a solvable system, all you have to do is rotate in the opposite direction. And so you can do this any number of times. It really doesn't matter what order you rotate the faces in. You can always return to that solved state, or a solvable position, by undoing the most recent rotation. And this is exactly the principle of strong induction, right? So you have that it was solvable for the first k rotations, and because you can reduce it to that p of k state by undoing that k plus 1 rotation, then it's solvable in that k plus 1 state as well, right? So it's solvable for any number of rotations. And so that's kind of the idea of strong induction, is that you can take advantage of previously solvable states, or previously known to be true states, to show that any future state is also solvable, or the proposition on any future state is also true. Okay, so that's strong induction. It's very similar to induction, but it's kind of going in the opposite direction. And so in that form, it relates a little more closely to recursive definitions, right? So a recursive function, or the inductive definition of a function, is one that's defined with 2 steps, as opposed to some closed form solution, like a line would be defined y equals mx plus b, right? So that's defined for every integer and for all real numbers and so forth, right? But a recursive definition wouldn't be as clean cut. So you would call the same function over and over again until you reduced it to that basis step, that initial term, right? And so for the example function, we've defined it with f of 0 is equal to 3, and then in exactly the way we tell students not to define terms in English, we have used the function itself in its definition, but it's still valid. It's still well defined, because we only define it going forward, and we have some minimal element, right, in a well-ordered set, that we kind of stop looking backwards with, right? And so we define it with the basis step, and then the recursive step, right? And so we continue looking backwards over and over again, right? So consider the value of this function at f of 4, right? Well, in order to get it the value f of 4, we need to know the value of the function f of 3. So then we look at f of 3 and we realize that we need to know f of 2. We look at f of 2 and we realize we need to know f of 1. We look at f of 1 and we find something finally that is well defined, right? So then we can compute f of 1 using this basis value, this initial value, f of 0, and we get our f of 1 term is 9, and then we can plug that in for f of 2, and we get that 2 times f of 1 plus 3 is 21. And so now we can plug that in to compute f of 3 and get that 2 times 21 plus 3 is 45. And now we can compute f of 4 using this value, and 2 times f of 3, which is 45 plus 3, is now 93, right? So that's the idea of a recursive function. And so that concept exists as we're programming as well, right? Like you're calling the function, is calling itself over and over again until it reaches some halting criteria, and the halting criteria would be this term, right? So you just pass in a slightly smaller value over and over again until you reach that basis term, that basic term. Okay, another example, which we'll run through pretty quickly, is the idea of rooted trees, right? So we discussed trees earlier in the semester, and if you have a collection of disjoint trees, each of them with their own root, so if you think about in terms of file systems again, you have directories and files. So directories or files could be leaf nodes, like there might not be anything below them, but the root would definitely be a directory, right? So you can create a new rooted tree by defining some new directory in this case, and then moving all of the other roots, all of these other directories, into that new top level directory, right? And that's really all we're claiming here. But regardless of what your directory structure is, you can continue to go up until you reach some highest level, right? And then you could construct a new rooted tree simply by creating a new directory and then moving everything else into it. So it's not such a an ethereal concept. Okay, so that's basically the idea of the connection between recursion and induction, and then we can look at some recursive algorithms, and we discussed binary search earlier in the semester as well, and so here it's defined in terms of C, and I'll share these lecture notes here in a little bit, possibly before this video is even posted. But the idea is that you have your collection of elements, right? So this is an array of sorted elements, of sorted integers, and then you define the minimum index for the array, which is 0, and then you define the maximum index, which it's so we've used size of here, and it's going to be 4 bytes in basically any system, and so the size of each integer is 4 bytes, so then we divide that by 4, right? So it's the number of elements times 4, one for each byte, and then we divide it to get the number of items. And then because we start at 0, we're 0 indexed, it runs from 0 to the number of items minus 1, and that's the maximum index, right? And we're looking for 56. So we pass in our array, our min index, our max index, and then the value that we're looking for, and we hope to get the matching index, or -1 in the case that it wasn't able to find the item in the list, right? So then we perform this operation recursively, right? So we take the average of the left and the right index, right, min and max for the range that we're looking at, and then we check to see whether or not the item at that position in the array, so halfway in the array, is the one that we're looking for. And if it is, then that average, the midpoint, gets returned, and that was where the item was found in the array. Otherwise, if it's less, because we're dealing with a sorted array, if the search value was less, or if the value that we are looking for is less than the value that was found at that midpoint, and we haven't already exhausted the list of possible elements, right? So if left is still distinct from that midpoint, then we call the function again, right? And this is the recursive step where we look in a smaller range. And so we now declare the maximum index to check the right index to be one less than the midpoint, because we've already checked that midpoint. And we don't need to adjust the left index because it's already bracketing the value that we're looking for. Right? We pass it in again. And then, so in this case, 75 would have been the first result. And now, in the second pass, we're looking at this set, 10, 34, 56, and 75. We pass it in, we take the average, we floor it, and the next item we check would be 34. Right? And it's going to miss again. And then this time the search value is greater than the value that we checked at that midpoint. So we call binary search again, and this time we move it to the right one. And so now we're looking from 56 to 56, right? So we're going to find that value at the midpoint, and we'll return it. But had we passed in 55, then the function would have still terminated. We still would have reached that base step and returned a value, but it would have been -1 for the index. And so this is an example of what a recursive function can look like whenever you're programming it. And the idea is that just as we were calling f over and over again from inside that function, now f is actually the function name. It's binary search here. Okay, so recursion is probably the nastiest subject that you'll learn in computer science, right? So I don't want to overload you by going through it too quickly, and I also don't want your eyes to glaze over too much. I would rather you watch what we've already covered multiple times than try to stack on too much. But again, I will post these notes for you so you can go over them. This is the same example in Java, and then one good piece of news in all of this nastiness of discussing recursion is that the functions that are defined recursively can be replaced by loops. So rather than calling the function over and over again, I know that can be confusing for some people. Through a little bit of clever work, it can be redefined into a loop. But I personally think it's actually easier to understand the recursive definition first and then come back later and learn how to adapt it to loops. But I do include that example for Fibonacci here. And then again, this time it's in Java for people that are more familiar with it. And then here we have merge sort, and y'all can glance over these, and it'll make a little bit of sense. But we'll go over them in a little bit more detail in the next class. I do want to spend one more class discussing recursion. But for now, that's it. Make sure you check e-learning for homework 6. It's posted, and then that'll be due next Wednesday. All right. Have a great weekend, everyone.